Okay, so welcome everybody for today's seminar. Today I have the pleasure of introducing you to Carlo Cannarozzo, who is currently a postdoctoral fellow at the Universidad Nacional Autónoma de Mexico. Carlo is mainly working on the study of early type galaxies, on the evolution of their scaling relations and kinematics, and their connection to dark matter halos. As we'll see today, he will show us observational data about the evolution of scaling relations in early type galaxies and their interpretation in a merger-driven evolution scenario with current state-of-the-art simulations. He did his studies in Bologna, where he got his PhD in 2021, working with Professor Carlo Nipoti and Alessandro Sonnenfeld. During his PhD, he was awarded with a Marie Curie grant in order to work with Professor Alexei Liotod in the University of Santa Cruz in the US, in order to specialize on advanced statistical methods and machine learning techniques to derive properties of galaxies. And then on March 2022, he moved to Mexico to work mainly with Dr. Aldo Rodriguez Puebla and Professor Vladimir Avila-Riz. So, Carlo, thanks for accepting the invitation. So you have approximately 45 to 50 minutes, which will be followed by a session of questions. So please, the floor is yours. You can start sharing.
Okay, thanks, Chiara. Can you hear me well?
Yes.
Okay. I'm sharing now. You should see my screen, right?
Perfectly.
Okay. So thank you, Chiara, for the nice presentation. Hi, everyone. As Chiara told you, I am Carlo Cannarozzo, UNAM fellow at the Instituto de Astronomía at the Universidad Nacional Autónoma de Mexico. And I do work in the context of early type galaxies and their merger-driven evolution, how scaling relations evolve as a function of cosmic time, and how stellar population settle in the final remnant of galaxies. And also I work in the context of the galaxy-halo connection, in both cases using state-of-the-art statistical and machine learning methods. And today I'm going to talk about some projects I carried out about early type galaxies, and if there will be enough extra time, I'm changed totally the topic, and I'll be focused in the last few minutes about a project I've been carrying out in the context of the galaxy-halo connection. So after an initial introduction, I'm going to the detail of first work and a comparison between MaNGA galaxies and the IllustrisTNG galaxies, and to understand the contribution of in situ and ex situ stellar population. Then I move in the context of the stellar mass velocity dispersion relation and how it evolves as a function of time, and also reconstructing the pathways of individual galaxy progenitors that we observe today in the present-day universe. And again, as I said before, if there will be enough time at the end, I'm going to talk about a method I've been developing to infer the mass of dark matter halo using machine learning. And then I sum up everything in my conclusion and take-home messages. So let's start with the introduction. We know from the lambda CDM model that after the Big Bang, from an homogeneous distribution, dark matter started to collapse under its own gravity into a scaffolding made of nodes, filaments, and surrounded by voids, right? And this framework is called the cosmic web. Baryons, after that, started to collapse following the potential well of dark matter, and gas clouds, cooling down their temperature, collapsed under its own gravity and converted them into stars and gave birth to the first generation of galaxies. But this is not the only gas reservoirs that a galaxy may have. Indeed, during its life, a galaxy may accrete from the surroundings cold gas inflows that feed the galaxy reservoir and enhance the star formation activity. And together with this accretion from the external part of the gas influence, the galaxy during its life may interact with other systems, with other galaxies, through galaxy accretion processes and minor and major mergers. And mergers can dramatically change internal properties of galaxies. Together with this scenario, another key protagonist of this movie is, of course, the central supermassive black hole. This central engine basically, through its activity, can accrete part of the gas and can blow out the gas, causing at some point a quench in the star formation. And basically, once all the gas reservoir has been exhausted, or better, the cold gas reservoir has been exhausted, the galaxy starts to experience a kind of passive evolution. And basically, the real only way to change internal properties is to perform again merger and interactions with other galaxies. The whole scenario that I've just described may take billions and billions of years, at the end of which we end up with these huge monsters that are early type galaxies. Morphologically speaking, this kind of galaxies are very simple objects. As you can see here from this picture, they are characterized by a very simple shape, elliptical or roundish shape. On the bottom left panel, you can see a color mass diagram drawn from Shavisky et al. 2014. This kind of plot is populated by both star-forming and early type galaxies. And even though this kind of populations populate the whole range of stellar mass and the whole range of colors, what we define is that early type galaxies tend to lie in the most massive tail, and also they tend to lie on the reddest part. And the fact that the early type galaxies are found in the reddest region of this diagram can be expressed as a combination of multiple factors, and in particular, the so-called age metallicity degeneracy. So indeed, if you focus on the right-hand part here, you can see on the top as a function of the stellar mass, the stellar metallicity, and on the bottom, the age. And if you focus on the red curve that represent the behavior of early type galaxies, at fixed stellar mass with respect to the star-forming galaxies, early type galaxies are found to be more metal-rich in stellar population, and the stellar population are very old. And these two factors combined together are the responsible for what is the red color of these early type galaxies. Historically, we know that early type galaxies obey some empirical scaling relations. From late 70s, it has been found that the luminosity, or analogously the stellar mass, is strictly linked to the velocity dispersion through the Faber-Jackson relation, through the size of the galaxy, through the Corbin relation. And soon thereafter, in the 80s, it has been discovered that actually both the Faber-Jackson and the Corman are just two projections of a more general relation where all the early type galaxies lie, the so-called fundamental plane. The entire formation and evolution scenario of an early type galaxies can be quite easily described under the so-called two-phase formation scenario of early type galaxies. Here, I drawn the sketch where you have on the x-axis the redshift, on the y-axis the mass assembly history. It means that you have the mass at given redshift relative to the mass that at the present day universe at redshift 0. In the first stage of its life, an early type galaxy is mainly composed by the in situ stellar population. So the fraction of stars that were formed in that galaxies from the conversion of the gas into stars, right? However, as a consequence of galaxy accretion processes, minor and major mergers, more or less from redshift 2 up to the present-day universe, the most dominant component that can reach even 70, 80, 90% in some cases of the total stellar amount is the ex situ stellar component. So that fraction of stars that were formed in other galaxies and accreted onto the main progenitor through galaxy mergers. And there is a plethora of possible way to understand that and to find evidence, pieces of evidence of this merger-driven evolution. For instance, one of them is that the study that we conducted with Nipoti and other authors in 2020, where we studied the radial distribution of the effective IMF, initial mass function. The effective initial mass function, as you can see here in this formula, is basically the ratio between the mass to light ratio that you observe in the real galaxies, or you assign in a kind of simulation as we did, relative to the mass to light ratio, assuming a given initial mass function as a reference, right? And we performed a set of binary mergers, dissipationless binary mergers, so without considering a gas that is an enough good approximation for these huge monsters. And basically, we performed these binary mergers with different mass ratios and also different orbital parameters. So that basically we perform these mergers head-on or with the presence of an angular momentum. And basically what we do find is that with respect to the radial distribution that is very steep for the main progenitor, here the red curve, all the galaxy remnant, so the combination of the two progenitors, the main and the satellite, has found to show a plateau in the innermost region. And this one is one of the unequivocal feature that is suggesting us that these galaxies undergo a merger-driven evolution. Why? Because actually it is informing us that the two stellar components of the progenitors are well mixed and are able to penetrate even in the innermost region and combine together homogenize the two stellar population. So after this introduction, I would like to start with one of the first projects that is my last first author paper that I've recently published, that is about the contribution of in situ and ex situ stellar population in early type galaxies, making a comparison between MaNGA observations and IllustrisTNG galaxies from the simulations. So the main problem when you observe a real galaxy is that you cannot say directly if that star or that stellar population was formed in that galaxy. So it's an in situ stellar population or was accreted through mergers as an ex situ. And so you have to rely on some peculiarities in the spectrum or analyzing the dynamics, and maybe you have to develop some models. For instance, here, or you can take a look at the other properties. For instance, here, as you can see, there is this sketch drawn from Oyarzun et al. 2019, where the author studied the radial distribution of the stellar metallicity for massive early type galaxies in the MaNGA survey. And they find that the innermost region is characterized by a steep phase, while the outermost region show a kind of plateau. And so they basically developed a toy model to explain the presence of this plateau in the outermost region. And according to their model, basically this plateau can be is due to the presence of ex situ stellar population accreted through a lot of minor mergers, and minor mergers basically settle their stellar population in the outermost region. That is why there is a plateau there. The other way is the one that I used to compare. And so basically, I compared the observed galaxies from MaNGA and the simulated galaxies from IllustrisTNG. And in particular, for the former, we provided an interpretative scenario following the merger tree of IllustrisTNG simulations to understand how in situ and ex situ stellar population combined in the present-day galaxies that we observe. As I was saying, I used MaNGA and IllustrisTNG. Why then? On the left-hand side, you can see MaNGA. MaNGA up to now is the largest survey in the present-day universe that mapped more than 10,000 galaxies using a special technique that is the interpretative spectroscopy. It means that when you observe with this technique real galaxies, you are able to peer the galaxy and you are able to spatially resolve individual region. And from each region, you are able to get all the information you need. The spectroscopy, the luminosity or the mass, the velocity of dispersion, and whatever you want. On the other side, we have TNG. TNG is the next generation of the original Illustris cosmological suite. It's a magnetotrodynamical cosmological simulation that mimics basically the formation and evolution of galaxy in a cosmological context. It counts of a different series of simulations and in three different boxes, TNG50, TNG100, and TNG300. The number stands for the side in megaparsec for each boxes. And for this comparison, we make use of TNG100 data. In this comparison, comparing observation and simulations is not easy at all for a lot of problems, right? And so we try to be as homogeneous as possible in selecting galaxies and making the things easiest. And so basically we selected from both samples, the observational and the simulated ones, galaxies with a stellar mass greater than 10 to the 10.5 solar masses, and we selected the early type galaxies on the basis of a color selection. So G minus R greater than 0.6. And we can do that because actually for IllustrisTNG, there is an official catalog of simulated colors that is mock colors according to the SDSS nomenclature, right? And so it's the same used for MaNGA. But what we did, basically, once we selected our sample, we compared the radial distribution of 4 stellar properties: the stellar mass surface density, the stellar metallicity, stellar age, and stellar velocity dispersion. For what concerns MaNGA, basically, we computed these 4 quantities in 5 concentric elliptical beams from 0 to kiloparsec out to the outermost region from 20 to 100 kiloparsec. For what concerns the stellar mass surface density, metallicity, and age, we relied on 2 estimates coming from 2 different stellar fitting codes, Firefly and Prospector. Instead, for velocity dispersion, we made use of PPXF. Concerning TNG, after doing a post-processing analysis of the data, we are able to get all this information, the 4 properties that I've just described, and we computed them again in 20 beams, concentric elliptical beams. But the good things of simulation is that you know the address of individual stellar particles, right? You know their ID. And so basically you are able to split the stellar population into in situ, again, the ones formed there in that galaxy, and ex situ, the ones accreted through mergers. And so we analyzed the radial distribution of these 4 quantities. For reason of time, I'm going to show you just the stellar mass surface density, but all the other properties are well retrieved from TNG. And so let's come to the result. These are how the stellar mass surface density profiles look like. Here we have 3 columns in 3 different stellar mass beams from 10 to the 10.5, 10 to the 11 solar masses, 10 to the 11, 10 to the 11.5, and everything is above 10 to the 11.5 solar masses. The first 3 panels in the top, basically compare the IllustrisTNG galaxy stellar population, the total stellar population, so in situ and ex situ, the black curves, compared with the estimates of stellar mass surface density from Firefly and Prospector, respectively the green square and the yellow dots. Instead, the bottom panels show just the analysis for TNG, where I split the role from the total profile of the in situ and ex situ component, respectively the red dashed and the blue dotted line. So if we focus for a moment just on the top panels, as you can see, over the entire range of radii in the 3 stellar mass beams, IllustrisTNG remarkably well reproduced the radial distribution of the stellar mass surface density for MaNGA galaxies from both Firefly and Prospector. And so the idea is quite simple. We can exploit IllustrisTNG mass assembly history to provide at least an interpretative scenario of how MaNGA galaxies, so basically galaxies that we observe in the present-day universe, assembled through the cosmic time. And so given that, if we split the role of in situ and ex situ, we can understand this scenario. Below 10 to the 11 solar masses, indeed, as you can see, the in situ stellar population is relevant at least out to 20 and 30 kiloparsec. Again, the in situ is the red dashed curve. But this scenario is no longer available above 10 to the 11 solar masses, because above 10 to the 11 solar masses, the ex situ component, the blue dotted curve, becomes as relevant as the in situ one, or even more relevant than the in situ one. And another aspect that you have to look at basically is that above 10 to the 11 solar masses, you can see that the radial distribution of the in situ and ex situ stellar components share the same shape. And this is one of the confirmation that this kind of galaxies underwent at some point a merger-driven evolution, mainly driven by major mergers, Why major mergers? Because major mergers are able to combine, even in the innermost region, the two stellar populations of the progenitors, right? And that is why also they share the same shape, because dynamically speaking, these stellar populations are totally homogenized together. But we want to do more than this, because we want to understand if it's true that these galaxies experience a major merger-driven evolution. So actually what we did basically was to reconstruct the mass assembly history of each individual galaxy in IllustrisTNG. And here in this plot, we have in the same three stellar mass beams, the distribution of the fraction of in situ and ex situ stellar population, the red and the blue distribution respectively. I don't know how many of you are familiar with violin plots, but basically violin plots are like histograms. So basically the larger the body of each violin, the higher the frequency on the y-axis. And as you can see here, we have a confirmation on the role of the ex situ stellar population above 10 to the 11. Because as you can see, above 10 to the 11 solar masses, the ex situ component, the fraction of the total stellar amount, is around 60, 70, 80% on average. So there is a huge contribution of the ex situ stellar component. But from where they come? Basically, we can study into the detail also the role of in situ and of the ex situ stellar component, disentangling if they were accreted through minor and major mergers, the green and the yellow distribution. And even though you can see that these distributions are very spread over the entire range of y-axis, what we define is that above 10 to the 11 solar masses, at least half of the ex situ stellar component has been accreted through major mergers. And so we have the final confirmation that, at least for IllustrisTNG galaxies, basically the ex situ component was accreted in a significant way from major mergers that allow to combine together the stellar populations. So in conclusion, in this work, basically we compared observed MaNGA galaxies with IllustrisTNG. We selected the ETGs as homogeneous as possible between the two samples, and we defined that actually above 10 to the 11 solar masses, the galaxies that we observe today, since actually the radial distribution of stellar mass surface density of IllustrisTNG remarkably well reproduced the radial distribution of the properties of MaNGA galaxies, above 10 to the 11 solar masses, as I was saying, these galaxies may be the result of a merger-driven evolution, mainly driven by major mergers that combine again the stellar populations in the final rank. And so now let's switch about the evolution of scaling relation, and in particular about the evolution of the stellar mass velocity dispersion relation. As I said at the beginning of this talk, actually it has been discovered in the late 70s, in the early 80s, that early type galaxies obey the Faber-Jackson, Cormendy, and the more general fundamental plane. And in the last decades, with the improvement of technologies, we are able to look farther and farther in the universe in order to understand whether and to what extent basically these scaling relations are still valid, and also if they do evolve as a function of time. For instance, here on the left panel, drawn from Van der Velde et al. 2014, we have the stellar mass size relation for the blue and the red galaxies, so for star forming and early type. And basically what we can see is that at fixed stellar masses, galaxies today appear to be larger than their counterpart at higher redshift. And in the past, there were some pieces of evidence also for the evolution of the velocity dispersion. For instance, here at fixed stellar mass, what we can understand is that the lower the redshift, the lower the velocity dispersion. And so, analogously to what was done, for instance, by Van der Velde in 2014 and other authors recently, we can try to reconstruct the evolution of the stellar mass velocity dispersion relation. Here, I draw the stellar mass velocity dispersion plane, where it traced to qualitative redshift reference, right? And so, at redshift Z2, that is higher than Z1. And if I put a galaxy at an early type galaxy at Z2, I can ask myself, how can this galaxy evolve to reach the functional form at redshift Z1? Basically, there could be three qualitative scenarios. Maybe it can increase its velocity dispersion, maintaining more or less the same, or decreasing its value. In 2020, in collaboration with Sonnenfeld Nipoti, we provided for the first time in the literature a description of how the stellar mass velocity dispersion relation evolves as a function of time. And to do that, I developed a Bayesian hierarchical tool to describe this evolution. We collected galaxies from the literature, homogenizing, of course, all the data, and we collected the early type galaxies with a stellar mass greater than 10 to the 10.5 solar masses over the range between the present-day universe, redshift 0, out to more or less redshift 2.5. Here you have all the details of of the various subsamples, but here, if you can focus on the stellar mass velocity dispersion plane, here I put all the galaxies colored as a function of redshift. And as you can see, there is a very clear trend for the evolution of the relation. So that basically at fixed stellar masses, the redder the color, so basically the higher the redshift, the higher the velocity dispersion. So as I was saying, to model the evolution of the relation, I relied on a Bayesian hierarchical approach that basically can be summarized in two main steps. There is a first step from which basically we fit the relation in the present-day universe. That in our case means fitting the relation for SDSS galaxies. From this fit, basically we got the normalization, the slope, and the Bayesian hierarchical tool allowed also to model the intrinsic scatter that actually is a quantity that usually often is not so considered in this kind of fit. So we got the normalization, slope, and intrinsic scatter, we put in our machine again, and we fit the rest of the galaxies at different redshift, considering two different families of models. On the one hand, we have the constant slope model, from which you can see here that there is an evolution just in normalization at fixed slope. The other family of models is the evolving slope model, for which both the normalization and the slope evolve as a function of time. In both cases, we accounted for sub-cases for which the intrinsic scatter is allowed or not to evolve as a function of redshift 2. So we analyzed this plethora of possible models, and among all these models we tested, we defined that the two best descriptions for the evolution of the stellar mass velocity dispersion relation are these two. On the left-hand part, you can see a constant slope model. On the right-hand part, you can see an evolving slope model. In both cases, you can see I traced 5 redshift curves from violet to red, from redshift 0 out to redshift 2. But let me stress the fact that with this approach, you are able to trace the evolution of the relation continuously without resorting to bending in redshift. As you can see from both plots, basically there is a clear evidence for the evolution of the relation. And in particular, to be just a bit more quantitative, a galaxy of around 10 to the 11 solar masses has on average at redshift 0 a velocity dispersion of around 160 kilometers per second that can reach even 207 kilometers per second at redshift 2. But now the question is, how a given progenitor of the galaxies that we observe in the present-day universe evolve in this plane? From these two plots, basically we can identify two qualitative scenarios. And it below 10 to the 11.5 solar masses, a galaxy, an early type galaxies from redshift 1 can increase, maintain, or decrease its velocity dispersion relation, its velocity dispersion to reach the functional form at redshift 0. But this scenario is not available above 10 to the 11.5 solar masses. In fact, a galaxy at redshift 1 above 10 to the 11.5 must necessarily reduce its velocity dispersion to reconcile it to the functional form at redshift 0. So in conclusion of this first part about the evolution of the stellar mass velocity dispersion relation, in 2020, we provided for the first time a description of how this relation evolves as a function of time, and we found evidence that it can evolve at constant slope or with a slope that gets steeper as the redshift goes up. But in any case, the intrinsic scatter is found to be constant at all redshift. But now the next step is to understand how individual progenitor evolves as a function of time. And so let's come to work that I've been conducting now, and I'm going to conclude very soon. It is about properly the reconstruction of individual galaxy progenitors to understand how they evolve over the stellar mass velocity dispersion relation plane. To do that, basically what I'm doing is to combine the inference from my Bayesian hierarchical tool with Empire. Empire is a semi-empirical model that is able to assign with a given probability a galaxy from observational recipes to a given halo from dark matter only simulation. And so following the dark matter simulation merger tree, basically we are able to reconstruct the evolution of individual galaxies and galaxy properties. In 2020, as I was saying before, we considered early type galaxies above 10 to the 10.5 solar masses and over the range between 0 and 2.5 in redshift. But now what I did was to enlarge my sample for two main reasons. I can explore a wider range in stellar mass, at least in the present-day universe. Of course, we included the Atlas 3D galaxy sample, early type galaxies, so that now we have a lower mass cut of 10 to the 9 solar masses instead of the old 10 to the 10.5 solar masses. And also we included a recent sample of massive early type galaxies between 3 and 4, so that we can constrain better the evolution of the relation either at higher redshift. So we have now the new sample of early type galaxy, and before filling again the relation, however, there is a kind of problem, because if we do focus on the subsample below redshift 0.2, actually you can see, so basically considering Atlas 3D and SDSS early type galaxies, you can see actually that maybe a single power law is not enough to model this relation, because there is a low mass tail that is very steep, then there is a middle range in stellar mass that is slightly shallower, and then there is a kind of plateau, a kind of saturation of the relation towards the higher mass tail. And so if one power law is not enough to model it, maybe it's better to introduce a new power law model that includes 3 power laws, right? And so basically I updated my Bayesian hierarchical tool on the basis of this new model and including all the new galaxies. And I ended up with this new model that is made of 15 hyperparameters. I know that 15 hyperparameters may sound a lot of parameters, and actually they are, but basically let me explain what these 50 parameters model. 7 of them model the relation and how it evolves. So the 3 power law models and how it evolves as a function of time. 2 of these hyperparameters model the intrinsic scatter and its possible evolution. But the other 6 hyperparameters actually model the prior on stellar masses, because actually our sample of galaxies is made of different subsamples with different low mass cut, different selection inside. And so these 6 hyperparameters allow us to model opportunely each subsample for the whole sample. And on the right-hand side, you can see the brand new relation of the stellar mass velocity dispersion relation. From the present-day universe, it starts with this triple power law model, but actually, as you can see, as the redshift goes up, basically the model collapses into a single power law at higher redshift. And why I decided to model this in this way? For basically 2 main reasons. If you are focused on the low mass tail at lower redshift, at higher redshift, actually the fraction of early type galaxies in the low mass tail at higher redshift is very low, more or less 0 on average, because actually this kind of region or this low mass tail should be should lie in this kind of region, start forming galaxies at higher redshift. For what concerns instead the high mass tail, we have also that the fraction, at least maybe before JWST and upcoming surveys, the fraction of stars of early type galaxies in the high mass tail is low at higher redshift. So basically, we have no available data here. So basically, what we did was to model the relation so that it starts as a triple power law and it collapses, it reduces into a single power law at higher redshift. And now, before going into the detail of how individual progenitor galaxies evolve as a function of time, I would like to say, show you an important impact that the new shape has in inferring the velocity dispersion function. Indeed, basically, if you basically convolve the inference of the stellar mass velocity dispersion relation with the stellar mass function of early type galaxies, you are able to trace as a function of time the evolution of the velocity dispersion function. And this is what we did basically. So we reconstructed our velocity dispersion function at different redshift, and here you can see a different redshift, but again, we are able to reconstruct it continuously without resorting to binning. You have the velocity dispersion function inferred in this way in these 8 redshift bits. And as you can see here, there is a comparison with some velocity dispersion function from totally observational driven from Besançon et al. 2012. And there is a very good agreement between my inference and the Besançon one. Right, but the cool aspect of the reconstruction of the velocity dispersion function is another. Together with the possibility of reconstructing continuously out to redshift for the relation, a cool aspect I've been finding is that the shape of the stellar mass function, of the stellar mass velocity dispersion relation you are using strongly depends on the shape of the velocity dispersion function inferred. Indeed, the continuous blue line here at redshift point 1 is the velocity dispersion function inferred from this 3-power law model. And as I show you, these kind of velocity dispersion function are well in agreement with, for instance, observationally driven inference from Besançon et al. But if you infer the velocity dispersion function just extrapolating to low mass tail, the classical single power law model, as I did in 2020, actually you end up with a velocity dispersion function with an higher normalization. So actually extrapolating a single power law to the low mass tail basically implies an overabundance of low velocity dispersions. So the message here is that it's you have to adopt a good, the best description to model the stellar mass velocity dispersion relation to have the good, the best estimates of the velocity dispersion function, and so how many galaxies we have per units of velocity dispersion. But the main analysis, the main aim of this study was, again, to reconstruct the evolutionary pathways of individual galaxy progenitors. And as I said at the beginning of this part, I used Empire. Empire, again, is the same empirical modeling model that Aldo Rodriguez Puebla has been developing for a while. Being a semi-empirical model, it means that it has a lot of observational recipes. Here you can see some of them listed: the stellar mass function from redshift 0 out to redshift 10, the main sequence star formation rate relation, luminosity function in far V, far infrared, size-mass relation and how it evolves out to redshift 6, and many other recipes. The wholly theoretical recipe behind Empire is that it accounts for the it takes into account for the merger trees of dark matter only simulations. These are the Bolshoi-Planck simulations and the multi-dark Planck simulation. Basically, Empire works in this way. You can assign with a given probability a galaxy to be like an early type or star forming with a given series of physical properties to a given halo. And so basically, if you reconstruct the merger tree of an individual halo, you are able to reconstruct the individual progenitor galaxy properties over time. This is, for instance, what Empire can do. Here we have, as a function of the redshift, how masses for a galaxy evolve. So we can reconstruct how the mass of dark matter, of course, evolves, but also the stellar mass, the mass of dust, how the black hole mass evolves as a function of time. And also we are able to reconstruct how star formation rate and black hole accretion rate evolves as a function of time. So combining my inference with the prediction made of Empire, I'm able to reconstruct the evolutionary pathways of individual progenitors. And here you have the final results. Here you have the brand new stellar mass velocity dispersion relation from redshift 0, the purple curve, out to redshift 4, the red curve. The colored region here encloses 80% of the progenitors of present-day individual galaxies, here marked from A to K. As you can see here in this plot, together with these colored regions, basically we have a gray region. What is this gray region? Actually, this gray region is marking a crucial threshold for the galaxy evolution. That is the so-called progenitor bias. What is the progenitor bias? It's a problem in the galaxy evolution for which basically, if I do observe a galaxy in the present-day universe that is an early-type galaxy, this early-type galaxy is still the Sun, the remnant of early-type galaxies at higher redshift, or at some point its progenitor are start forming. So basically, this kind of region is marking a region below which at least half of the progenitors of the galaxies in the present-day universe are still early-type galaxies. So, of course, we cannot rely on the evolution or here clear in the shaded region. We cannot rely for what is above the progenitor bias mark. But of course, because there are star-forming galaxies there, at least half of the 50% of the progenitor are star-forming. And we know that actually star-forming should lie at fixed stellar masses to a higher normalization. But of course, everything that is below this region is something that we can rely on. And so basically from this reconstruction, we can identify three different regimes of how the stellar mass velocity dispersion relation evolves as a function of time. From K to G, so the low mass tail, below more or less 10 to the 10 solar masses, the velocity dispersion tends to increase as a function of time. Then in the middle range, from F to E, the velocity dispersion is on average more or less constant. However, above 10 to the 11 solar masses, from D to A, the most massive tail has found to decrease dramatically its velocity dispersion to reconcile it to the functional form. So basically what we define is that there is something that pushed down the relation in the high mass tail that actually allows also to decrease this velocity dispersion. And so to understand better what is behind and what causes this kind of flattening in the high mass tail at redshift 0, I have reconstructed, as I did for IllustrisTNG galaxies before, the merger tree of galaxies in Empire. And so basically here you have again the violin plots for each set of galaxies in the present universe, again from A to K, and I split the role of in situ and ex situ stellar population. And as you can see, the cool thing is that where the relation starts to become flatter is probably where the ex situ stellar component starts to become relevant. And so the high mass tail, as you can see here, C, B, A, start to reach even 80–90% of the total stellar amounts from ex situ. So basically, this is a hint that basically what causes this flattening is the accretion through minor and major mergers of the ex situ stellar component. But now I would like to understand whether the role of ex situ coming from minor and major mergers are the two most relevant. And so I split again here the role of minor and major mergers, but now you are seeing discrete distribution because these one are just histograms. How many minor and major mergers on average these galaxies experienced? And basically, as you can see here, the most massive tail, in particular B and A, underwent during their life a lot of minor and major mergers, on average 4 in the redshift between more or less 2 and the present day universe. And so basically the high mass tail can be again the result of a merger-driven evolution, mainly driven by major mergers, that in some way is pushing down the relation, making it saturated at the low mass tail in the present day universe. So in conclusion of this work, basically, I provided a brand new model that now is not a single power law, but it starts in the present day universe as a triple power law model. The shape of the stellar mass function, its evolution, dramatically change the shape and evolution of the velocity dispersion function, as I was saying. And in particular, we constructed the evolutionary pathways of an individual progenitor in the present day universe. And the relation basically is shaped a lot from the kind of mergers these galaxies experience. So this work is still in progress. It will be submitted pretty soon to NRAS. But in the next future, what I'm going to do is to extend the analysis to have a more complete view, a 360-degree view. I'm going to extend the analysis to the size-mass relation and its evolution, because as you can see here again, from considering galaxies below redshift 2.2, there is this clear trend with this triple power law model. And also I would like to understand how the fundamental plane behave, to understand properly how the progenitors rebalance the size and the velocity dispersion in this brand new model. And of course, in the future, I would like to extend the analysis to start forming galaxies, because as I told you before, everything where below the progenitor bias mark is, we can rely on it, of course. But star forming, we know that lies on a higher normalization. And so basically, I would like to extend it to have a complete view of how this scaling relation evolve as a function of time. So I don't know if I have enough time. I don't know,
minutes probably.
What?
A couple of minutes.
Okay, in the last few minutes, I would like to change totally the topic. It's just an extra of another project I've been conducting that is about the inference of the mass of dark matter halo using machine learning. As I told you in the beginning, basically dark matter halo is what led basically the formation and evolution of galaxies. And we know that actually there is a strict link between dark matter halo and the galaxy itself. And this is the galaxy-halo connection. For instance, we know that the most well-known relation studied is the stellar mass to the halo mass relation, or we know also that the size of the dark matter halo strictly relates with the size of the galaxy itself. However, in this scenario, you have to be reminded that many physical properties may interact with may show other relations with other physical properties. We know, for instance, that the stellar mass is related to the supermassive black hole mass, or to the stellar metallicity, or to the gas metallicity, that in turn is connected to the star formation rate. And again, the black hole accretion rate and star formation rate combined together are predictor for the mass of dark matter. And so basically, at the end, you end up with this very intricate network of possible relations. And so machine learning, in this sense, can help us to shed light and to understand which are the most predictors for the mass of dark matter halo. This is the aim of this work. I would like to find a functional form at the end able to predict the mass of dark matter halo using all the data sets you have available from your surveys, right? And to do that, basically, I've been exploiting this state-of-the-art machine learning tool that is in the context of the generalized additive models with pairwise interactions. Basically, when you have your data sets, the quantity one would like to infer, that in my case is the mass of dark matter, can be expressed as a summation of two kinds of functions, the 1D and 2D shaped functions. If we do focus on the sketch on the 1D shaped function, on the x-axis, there is a feature from your observation, let's say the stellar mass. And on the y-axis, you have a score. The score is a quantity in units of the mass of dark matter, in my case, that you have to add or subtract to make the inference of the mass of dark matter. But of course, you have to be reminded that you have all the other properties all the other features that are modeled. So each feature had its score. And together with these, you have the 2D shape function. So you have the cross correlation between two features. For instance, I don't know, the stellar mass, and on the y-axis, there could be the black hole mass. And in this case, in this heat map, there is the score. And so basically what I'm doing now is to train this model based on IllustrisTNG cosmological simulation. In the last few minutes, I'm going to show you briefly the results based on redshift 0 galaxies using these 7 properties. So training the model on IllustrisTNG galaxies at redshift 0, this is what the model learned. This is a bar chart that is telling you which are the most relevant features useful to infer the mass of dark matter. As you can see, all these contributions and even the 3 most relevant pairwise interactions here indicated by the cross are helping the inference. But of course, for instance, the gas mass, the stellar mass, the star formation rate, etc., are the 3 most relevant features able to predict well the mass of dark matter in the present-day universe. And just to make you understand easily what's the strength of this kind of model, this is, for instance, the 1D shape function I was mentioning before for the stellar mass. How can I use this kind of information from this kind of method? This plot will show you the stellar mass range explored in TNG 100 at redshift 0. Again, on the y-axis, you have the score, so in units of the mass of dark matter. Score 0 corresponds to 10 to the 10 solar masses in mass of dark matter. And so how can I use this plot? Basically, this plot is telling us that to make the final inference of the mass of dark matter, a galaxy of around 10 to the 7 solar masses had its contribution of around minus 0.5. A galaxy more massive of around 1012 had a contribution of 0.9 dex to the final inference. Again, this is just the inference made on the basis of the stellar mass, but you have to be reminded there are all the other features and all the other pairwise interactions. The cool thing of this method is that, as you can see here, this function is not a notorious function, is not a linear function or a polynomial, but it's a very complex function. There are plateau, jumps, hump-like structure, and it's totally up to the user to understand what is the meaning of each individual feature. And for instance, here, around 10 to the 11 solar masses, there is this hump-like structure. And what is informing us? Basically, it's the result that I showed you before. Here is happening something that is related to the transition around 10 to the 11 solar masses between the role of the in situ and ex situ stellar component. So this method is very informative to understand how individual subset of each feature is helping you in making the inference. So together with the stellar mass, as I was saying, you have now the n-dimensional problem, extending the analysis to each projection for each individual feature. And here you have the example of the pairwise interaction. So basically, you trained your model, and now you can test your prediction on your test sample. And what is it found is that this method is found to be very promising in this aim to predict the mass of dark matter. Because as you can see here, there is the one-to-one comparison between the mass of dark matter from the simulation and the mass predicted from this method. And as you can see, it follows perfectly the one-to-one relation with a very low scatter. So this method is found to be very promising to predict the mass of dark matter. And the other cool aspect I've been analyzing is to extend the analysis at higher redshift and at other simulation in order to understand whether the strength of each feature change as a function of time and also as a function of the resolution and the kind of cosmological simulation you're using. And for instance, here you have the bar chart I showed you before, but now it's not at redshift 0, but it's at redshift 3. And some of these features are again in the same position, the gas mass and the stellar mass. But now there are some features that went up as a function of time. For instance, the stellar metallicity was one of the last at redshift 0, but for some reason at redshift 3, it starts to be one of the best predictors for the mass of dark matter. And so here you have, for instance, how the score profile for the stellar mass, the ones that I showed you before, evolves as a function of time. So there is a change of slope and the change of normalization. And as I was saying, now I'm going to involve other simulation. I started with the whole subset of the TNG cosmological suite, TNG 50, 100, and 300, in order to understand whether and to what extent basically different cosmological simulation with different models, with different boxes, with different resolutions, may differ also in the inference of the mass of dark matter. So this one is a work in progress. It was just my aim to show you this preliminary result. I leave you here with the conclusion of the whole talk. But before going on, I would like to say that together with Mireia Montesquiles and Salvatore Quai, we organized this special session for the next EAS 2023 that will be held in Krakow, Poland, from 10 to the 14th of July 2023. So next summer, about the importance of relation in galaxy evolution, linking what is the observation and theory in the so-called big data era that we have been living. The deadline for submitting abstract has been postponed by 1 week. So basically it was yesterday, the deadline, March 1, but now the deadline is March 8. So if you are interested, we are totally pleased to receive your abstract. And we hope to meet you in person at EAS 2023. So I leave you here with my conclusion, and thank you very much for inviting me and for giving me this great opportunity. And sorry to cannot be there in person. Thank you very much.
Thanks, Carlo. I don't know if there are any questions. There will be time for a very quick question, probably, either in the aula or online. Either, yeah.
So thanks for the talk first. And this is a question about the first part. So if I understood you correctly, you're saying that the high mass end ex situ star formation dominates in situ star formation in early type galaxies. Okay. Now, if that thing, and this is a naive argument, but if that thing would be correct, I would expect that the stellar metallicity at the very high end would be smaller than at the intermediate masses, simply because the progenitors are low mass galaxies. And so far as I'm aware, this is not observed. Could you comment on that?
I can't hear you so well.
Sorry,
can you
I'll try
the last part? Sorry.
No. So if the stellar population is dominated by mergers,
Yes.
the progenitors of the most of the stars are going to be of low mass. So the stellar metallicity is expected to drop when you go to very high mass galaxies, simply because the progenitors are of low mass. And I was saying that this is not observed. So I would like to know your comment on that.
Yeah, basically, according to what IllustrisTNG is predicting, right, from the evolution of the simulation, actually this is not probably the scenario. It's IllustrisTNG. It's very in contrast with some previous work in the literature made on simulations, for which the galaxy that we observe today instead are created through are formed through a lot of minor mergers, right? And so it's in line with what you are saying. This is, for instance, I had no time to show you, but this is how the stellar metallicity profiles looks like, right? Here again, you have for the 3 stellar mass bin on the top the comparison with the stellar metallicity, and on the bottom the role of the metallicity between in situ and ex situ. What is it found in IllustrisTNG is that basically, in particular above 10 to the 11 solar masses, as I was saying, this kind of galaxies are assembled through a merger-driven evolution, mainly driven by major mergers. And the fact that these are major mergers, it's informing us in this case that the progenitor of the galaxies that we observe today should be more or less similar to each other. Indeed, as you can see here, above 10 to the 11 solar masses, the stellar metallicity predicted by the simulation by IllustrisTNG, the ex-situ component is found to be even more metal-rich than in situ. And the reason why it is happening, it's at least for what concerns IllustrisTNG, is that the two main progenitors are similar to each other. So you are combining a stellar population that are more or less the same. So keeping apart the in situ stellar component that evolved through cosmic time and at some point it relaxed, the fact that the ex situ is found to be more metal rich is probably because in this scenario predicted from IllustrisTNG, that again is in contrast with some of the previous scenario from previous simulations, like Nabos, etc. Basically, the ex situ component in stellar metallicity is found to be more metal rich, probably because the progenitors share more or less the same kind of stellar population. So it's in contrast, of course, what you say, but it's probably because IllustrisTNG predict a different scenario of how these galaxies assemble through cosmic time.
I'm just going to check whether we have extra comments, probably not. Just as a final question, actually, I had one. I was wondering whether you are also planning to check the effect of any rotational component on the measurement of velocity dispersions and probably on the evolution of the scaling between the stellar mass and velocity dispersion, because for example, at the moment, there are no ways of constraining extra rotation that might affect the stellar velocity dispersion measurements, at least observationally. So I was wondering if you have any future prospect to try to address it from simulations.
Yes, thanks for the question. Basically, as I was saying, this particular work was focused on early type galaxy. And so actually it's something that we are not taking into account basically. But of course, in the case of extending the analysis to star forming galaxies, that again, as I was saying before, should lie at higher normalization at fixed stellar mass with respect to early type galaxy progenitor. Of course, taking into account for the rotational components, all the dynamical components, basically, it could be much more informative in this sense. So in that case, when I involve even star-forming galaxies together with modeling the evolution of the stellar mass velocity dispersion relation, so the Weber-Jackson, I could analyze also the evolution of the of the Talby-Fisher to have a more complete view. It's something, of course, that it's not the interest of this particular study, but it's something that I'm planning to do in the next future.
Okay, thanks. Just to mention, because at least for high redshift quiescent galaxies, then there is a debate whether they actually look like fully spheroidal galaxies or
disky. Yeah.
disks. I mean, that might perhaps explain some of the points that have very large velocity dispersions that
yes.
are not. But anyway,
yeah, such as the galaxies that I'm taking into account now from the subsample from redshift 3 from Forest et al. 2022. Yes.
Yeah, fantastic. Okay.
Yeah, absolutely.
Thank you.
Yes.
Thanks. So I'm afraid we have to wrap it up.
Okay.
So thanks a lot, Carlo, for joining. And if there is, so there is, I think, probably a comment or a question from a chat. Mark Baltzer's comments.
Yeah, I had a quick question.
Yes.
If there's time, I will ask it. Thanks for the talk.
If we're already off time, but if it's quick, probably.
Yeah, the question was really very interesting. The relative importance of major versus minor mergers, and I was wondering. What is whether there may be a resolution effect in the simulations, that would make smaller galaxies not survive the tidal fields and therefore not make it in the mergers due to resolution effect. At some mass, this must happen. And what would be the mass limit at which you start losing low mass satellites before they emerge?
Yeah, thanks for the question. I would like to say about the resolution very briefly that, of course, here we are focused on the massive tail, right? So, of course, everything is above 10 to the 10.5 solar masses. So in terms of this kind of resolution, we should not be affected at all, right, from this kind of inference. About the role of centrals and satellites, I would like to say that we started the radial distribution, disentangling even the role of centrals and satellites, finding that actually there is no difference at all between all the properties, of course. And this is something related to the answer that I said before. The fact that satellites and central galaxies share the same behavior without finding any significant difference is something that is telling us that the progenitors of this kind of galaxies, satellites or centrals, are more or less the same kind of galaxies. About a very last comment about the resolution, here in each profile, I don't know if you can see here, but basically here there is an hatched gray region that is marking the resolution in the innermost region. So out to 2 kiloparsec in the very innermost region, around 2 kiloparsec, basically it's not under control, of course, even though even in this region, as you can see, the radial distribution of IllustrisTNG is well reproducing the MaNGA galaxies. But everything is above this threshold, so beyond the 2 kiloparsec is totally under control. So I don't know actually if it's something related to the resolution. It's something more related to the whole model implemented in the IllustrisTNG simulation, and for instance, in the agent feedback, the recipes for star formation, and how the feedback impact in the evolution of the galaxy itself.
Yeah, thanks.
Okay, so let's wrap it up. Thanks a lot, everybody, for joining, and see you next time. Thanks, Carlo.
Thank you. Thank you very much. Bye.
Bye.